Hello everyone, welcome to the EasyPower Tuesday Refresher. Today's presentation is part 2 of the overall topic of coordination and arc energy reduction as it pertains to the National Electrical Code. My name is Jim Chastain. I'm apps engineer at EasyPower, and I want to welcome everyone to today's presentation. Should be fairly well packed with information, and be more than happy to address questions as time is allowed. And I'd like to start with a couple poll questions. Again, no obligation or liability, but I would appreciate some feedback as to where people stand on the topic. And the first question is, what or which type of device causes you more concern when dealing with arc energy reduction? Just kind of make your entry on the screen. Again, we appreciate everyone attending today. I make no claims of being an expert on the National Electrical Code, and for that matter, I'm not an expert on the hardware that's used to that we're going to be discussing. And so my primary focus is on EasyPower's ability to reflect or simulate how these different pieces of hardware can achieve the recognized response. So it looks like we have a quorum here. So here's how folks have weighed in on this one, with kind of evenly divided. And multi-case circuit breakers are admittedly a problem area. And then the second question is, how often or how frequently do you utilize TCC plots? And again, there's no right or wrong answer, just kind of curious how people deal with the issues currently. The topic is fairly well, I guess, open to interpretation, and some of the regulations or some of the implementation has been forecasted for several years. And so what we're seeing with the timeline or the deadline that was imposed in 2020, that was given the manufacturer some time to come up with some solutions. We're starting to see those find their way into current designs. So here's how people have weighed in on this. Glad to know that most people are fairly familiar with the TCC plots, so let's kind of start from there. Okay, thank you again for attending. What we're going to be focusing on today are two particular articles, and they have kind of the same overall organization as far as information. The first is the article 240.67, which applies to fuses rated over 1200 amps. As I mentioned, it originated in 2017 with an effective date of January 1st, 2020 to give the industry time to create products to address the requirements. And there's three general areas in the article. One is documenting the method chosen to reduce the clearing time and make it available to those that are responsible for installation, operations, or inspection of new construction. And then B is there's a list of specific methodologies that are acceptable, with the margin or the deciding point as any fuse that does not clear within 0.07 seconds, then it has to follow one of these reduction methodologies. And then thirdly, the need to include performance testing as a measure of ensuring the results have been achieved. So again, it only applies to fuses rated over 1200 amps or greater and with clearing time of 70 milliseconds at the arcing current. So there's quite a bit kind of built into this statement, and it's easier to appreciate if you look at the TCC curves. The methodology that EasyPower uses to calculate the arcing current is detailed in IEEE 1584, and part of that standard is the consideration of determining both an arcing current based on the bolt or fall current and a reduced arcing current based upon correction factors that are particular to that particular installation. And then finally, beyond 106,000 amps, which is the limit or scope of 1584, EasyPower uses Raufli method to determine instant energy. So with that caveat, I wanted to just run through a real quick example here. This is a display of, and the reason to kind of focus on this is we're showing the operations of several different fuses at several different voltage fault currents and the resulting instant energy. And the technique here is to use a virtual connection, whether there's a tied connection or not, so I can show different independent utility sources. But what we're looking at is anything that's 0.07 or faster, which includes these two middle fuses. There's no further action as far as mitigation required as far as the standard. So let me kind of open up this example and we'll talk about it. And again, what we're looking for is the instant energy due to the arcing current in that particular phase or that particular supply. So right now we're looking at the total available bolted fault current, which includes the upstream supply and any motor loads that are connected from downstream. And by displaying this spreadsheet, we can see that, again, the clearing time for these two, the 1500 amp and the 2000 amp, the way at least it's set up, is clearing at 70 milliseconds and 69 milliseconds. So these two do not need additional mitigation. Now, and it's point worth noting, at 106,000 amps of bolted fault current, that's outside the scope of IEEE, but because we've selected the Raufli solution, when we go to Arc Flash in EasyPower and look at the advanced controls, when the current exceeds the IEEE maximum, we've selected to utilize the Raufli method. If we unselect that, and this is just a point of order, and fault the buses again, we see that results are not indicated, and that's because there's no recommendation within IEEE on what to do with that. And so the tool allows me. So there's a couple points I want to make from the display. First of all, the bolted fault current is the total available current on that particular bus, and then the branch is the control or the path that's going to control the timing device. And so when we're looking at a trip time, that's going to be based upon the arcing current in that particular branch. The fact that these are all magenta, and I'm going to go back and turn on my Raufli equation just to include it in the discussion. And again, it's outside of the range of IEEE. But the fact that these are all magenta colored, that means that the tool and the calculations for correction factor have utilized the reduced arcing current for these calculations. And so that's the way that the current is known. So anyway, at this point, we know we need to have some mitigation for the 1200 amp circuit and for the 2400 amp circuit over on the second from the right. Okay, so what that entails now is part of the regulation. So any fuse having a clearing time of 70 milliseconds or less is not subject to these restrictions. But one of the following methods for anything outside of that bound range can choose from differential relaying, energy reducing maintenance switching, energy reducing active arc flash mitigation, current limiting electronically actuated fuses, and an appropriate equivalent means. Well, and we'll get into an example of these more so when we get into the breakers. But what the discussion is, if we have differential relaying, we have a relay installed in the system that's comparing the input current to a particular zone, and then the output of the feeder system to my loads and can determine a relatively small differential, excuse me, can trip on a set point of relatively small differential so that it can detect a fault early in the process. And so the methodology that's the hardware that's being presented basically has a fusible switch that allows us to detect the fault and then open up the fuse quicker, or open up the switch quicker than the fuse that's installed can respond. Likewise, with an energy reducing maintenance switch with local status indicator, again, the fuse is equipped with this maintenance switch, which provides protection for downstream faults that are greater than its pickup value of the fuse by itself. The point being is that we need to respond quicker than the 70 millisecond limit, and there's no specifics on what that needs to be. It ends up being a conversation between management and their technical resource as far as recommended energy levels that we're going to be working under during this period. So some examples of some of the new equipment that's showing up on the market include the capability of not only doing energy reduction through these different methods based upon relays that are included, but also have the ability to include ground fault protection. And if you look at their application note, again, what they're suggesting is that there's a fusible switch that responds to the relay settings, and if that fault current is determined to be a identifiable recognized fault, then it would respond quicker than the fuse by itself would. Now, in EasyPower, for several years now, we've had what we call relay controlled fuses, where the switch is in parallel to the current limiting fuse, and the difference here is to open up the low resistance current path and let the fuse respond accordingly. So the alternative is to put these in series, open up the switch and not have the delay of a current limiting fuse. At any rate, the different pieces of hardware are just now coming out. EasyPower can include in the library, and would be more than happy to specialize or detail any particular TCC curves that are included. And so it's just a matter of requesting the model be set up. Now, when it comes to breakers, a very similar restriction, and the guidance here is where the highest continuous current trip setting for the actual overcurrent device in a breaker is rated or can be adjusted at 1200 amps or higher. And then again, the documentation method and the list of the methods to reduce clearing time and performance testing is also included in 240.87. Now, the instruction is that it must be set to operate at less than the available arcing current. The definition of available arcing current includes a maximum setting, but as we saw in that first example, reduced arcing current could be a more restrictive data point in terms of instant energy. So the list includes zone selective interlocking, differential relaying, energy reducing maintenance switch, again, very similar to the fuses. And again, these, for the most part, are, well, and so I'm going to run through these. These are already included in EasyPower. So zone selective interlocking pertains to a system whereby I have a communication link between several of the breakers, and by so doing, I create a setup that the system can determine the location of the fault and then isolate and back up that particular fault if necessary. So this looks like this. And it's more effective if you look at the TCC plots. So here I have my breakers set up, and in normal operations, if I fault all the buses, I have instant energy that exceeds at least company policy for doing maintenance work. We have 9 calories on this panel, 26 on this, 15 calories, and then 28 on the master switch board. By selecting or implementing zone selective interlocking, by turning it on, what this allows us to do now is to work with protection that's rated at 2.5 calories or greater, 4.0 calories, 4.0 calories, 4.5. And again, the advantage is more easily identified if we look at the TCCs. So what I'm going to do is display this one breaker, which is connected to my main, and the feeder, display the TCC curves. And now when we look at the trip characteristics of a fault on this particular bus, I'm going to fault all the buses first. I didn't get my main breaker in there. Sorry about that. I'm going to pick up the main and the feeder breaker and plot the TCC curves. And so we have a coordinated situation where if we have a fault on the downstream bus, the BL2 will trip first, and then BL1 will back it up if the BL2 does not trip. Now, if we have zone selective interlocking, and again, this gives us the higher instant energy if operating in normal operations. Now, if we apply zone selective interlocking to this system, and we see a fault on this bus, it will respond quicker, recognizing that there's a fault downstream without any effect on BL1. If we go back to normal operations and then have a fault on this bus, we can see the upstream breaker trips quicker. So the operation of the breaker itself, the breakers themselves, change based upon the zone selective interlocking being engaged. The advantage is you maintain coordination during normal operations. So there's the disadvantage is you're not really sure unless it's been verified or tested, you're not really sure when zone selective interlocking is engaged. So that's zone selective interlocking. Then differential relaying, again, is very similar to fuse control, except instead of a fuse being switched, we have a main breaker that's going to be protecting the whole system and will trip based upon the differential signal being smaller. Now, in EasyPower, we can't simulate the reduced voltage differential and the small signal that can be applied. And so in terms of EasyPower, we have to just state in the setup of the bus system, here's my differential relay, and we're comparing upstream of the transformer and downstream of the feeders, and we're protecting this particular bus. In my database edit, as I set up the arc flash determination, I can see that when the relay is a protecting device, it will respond in 25 milliseconds. And so this is the number that's utilized for calculating the instant energy. And so if I have a fault on this bus, you could expect to see basically a response of either the fuse or the upstream relay. So that's a differential relaying. Energy reducing maintenance switch with local status indicator is very popular and has been in the industry in breakers for over 10 years. And again, it's similar to the operation of the fuse, except instead of operating a fusible switch, they're tripping more likely the main breaker or the main switch for the system. And so this is similar in many ways to a zone selective interlocking, with the difference that it disrupts, or it doesn't support coordination or maintain coordination. And it's important to have the status indicator. So if we go to short circuit, fault all the buses, we get a normal operation with elevated instant energy. If we go to maintenance mode and set it on, then we have a quicker response and consequently lower instant energy. And again, it's helpful to look at this in the TCCs. So if I go back to my normal operation, and we can select the breaker and a couple breakers in a relay, plot the TCC curves, we can see that in normal operations, if we have a fault downstream, it's going to be this magenta breaker, FDR1, that trips first. And if we hover over the bus, right-click, I need to hover on the bus, and insert arcing tick mark, we see here that the worst case, at least for this particular setup, is 100% arcing current, and the instant energy is calculated based upon the time that's indicated where that little triangle, which is my arcing current, crosses the upper boundary of the trip curve. Now if I turn on maintenance mode and we have a fault at that location, now the breaker will trip this much faster, and for that same arcing current, the instant energy is calculated based upon a time of 40 milliseconds, which is about 15 times faster than the normal operations. The disadvantage is we get the response from the main as well, and so it could end up being a race between which one trips first, and the only downside is we've lost coordination at the same time. Now the good news is there's the potential for retrofitting some of the trip units that have these capabilities in them. So then there's the potential for using energy reducing active arc flash mitigation system. And this is referring to, rather than current sensing, but light sensors that can be placed anywhere in my system and protect that particular element or subsystem, and can respond quicker than the reaction time to current. And so they're cleared with a specific delay as long as it's greater than the pickup point of the active mitigation system. So again, this can be in relatively short amount of time in terms of 10, 15 milliseconds, and be able to get a very quick reaction time. And again, this is set up in EasyPower similar to the differential, because we can't simulate the light sensitivity, and so that's how it's implemented in EasyPower. Now, and the fifth element that's recommended is an instantaneous trip setting. Now, this is due to the fact that normally in main and upstream breakers, the recommendation is to avoid an instantaneous trip because it interferes with the multi-case circuit breakers, which have instantaneous trip settings closer to the load. And so one way to mitigate the instant energy is to utilize the trip setting for that device, which may be upstream. Again, the downside is you could be losing some coordination properties. Now, the one adamant thing is you can't temporarily adjust the instantaneous trip setting to achieve energy reduction manually. And so there's a fair amount of concern about thinking that that's the way to do it. So again, it's not something that's permitted. One thing that comes up, and I've heard this referred to in several discussions I've had, and that is now that barriers shall be placed in Article 230.62C, requirement that barriers shall be placed in service equipment such that no uninsulated, ungrounded, or service bus bar or service terminal is exposed to inadvertent contact by persons or maintenance equipment while servicing load terminations. The specific purpose of this is to prevent electroshock, and so the barriers often, at least temporarily, prevent inadvertent contact with the skin or some non-protected part of the operator. The concern or the confusion is this is not a definition of a flash barrier, which is interesting because, or it's an arc flash barrier. The lack of an arc flash barrier suggests the need to exclude the breaker for calculating instant energy. Now, while it's true that putting a barrier, electroshock barrier on there reduces the potential for accidental contact and one of the higher sources for arcing flashes events because of personnel mistakes, it's still technically not an arc barrier. So these plastic strips that get put on terminals technically don't qualify as an arc barrier to determine whether we include or exclude the main breaker. And so the same discussion about instantaneous override. So the question is, how do we achieve selectivity with thermomagnetic breakers? It's not easy. Again, some of this is the coordination. If there's a tested coordination between breakers with instantaneous settings that the manufacturer can support, that can be included in the design. But the recommendation is you need to have the instantaneous override set high enough that it make sure you don't, in other words, the instantaneous stripping on a downstream bus doesn't protect the main breaker or the switch gear above the fault in any of the other sister loads. So the protection of somebody working on, in this case, the internal bus, having an instantaneous breaker downstream doesn't protect me from a fault on the bus itself. So the need to have an instantaneous strip setting on the main is part of the discussion. And yes, you're going to have a problem with selectivity, and there's no recommendation on how to deal with that from the National Electric Code. Okay, so apologize for some of the wishy-washy discussion, but there is a fair amount of room for engineering judgment, and that's I think what's being guided here, is that there's no direction on the instant energy that you need to achieve, just the fact that the equipment needs to be included based upon this criteria of 70 millisecond being the long trip time. So so the other question that came up is, how similar is this equipment to the little fuse arc flash relay system? I think it's very similar. There's a lot of commonality in the switchable fuse, and it really depends upon if you end up using one of these newly constructed protective switches in your installation. By all means, if we can make available the TCC curves and the discussion of how the relay works, we'd be more than happy to model it in the EasyPower device library. Appreciate folks attending today. Certainly, if you have any questions, shoot me an email at jim@easypower.com, and we'll make a PDF copy of the presentation posted along with video. Appreciate for running long, but I hope you guys have a good day, and we'll talk to you later. So long.